How quantum is used today. Quantum computers already exist, but they are not replacing laptops or running everyday apps. Instead, they function as highly controlled research tools. And that distinction is essential for separating reality from hype. Cloud-based quantum access. Most users never physically see a quantum computer. Systems are accessed remotely through cloud platforms such as IBM Quantum and AWS Braket. Users write programs, submit them online, and wait for results. This model exists because quantum hardware is extremely fragile. Machines must operate near absolute zero and remain isolated from environmental noise. As a result, they are housed in specialized laboratories rather than homes or offices. Access is also shared. Multiple users rely on the same devices, creating queue systems where jobs may take minutes or longer to run. While slower than classical computing, this approach protects hardware, prevents misuse, and enables global access. Simulators and why they matter. Surprisingly, most quantum work happens on simulators instead of real machines. Simulators are classical programs that mimic quantum behavior, allowing researchers and students to test algorithms, debug code, and explore new ideas. This is important because current quantum computers are still small, noisy, and error-prone. Running experiments on real hardware can be slow, expensive, and unpredictable. Simulators provide a stable and flexible environment, making them essential to progress. Rather than limiting the field, they support learning and innovation while hardware continues to improve. Researchers are also exploring practical applications in fields like chemistry, optimization, and cryptography, though these uses remain experimental. Companies and universities collaborate to test small-scale problems, building knowledge for future breakthroughs. For now, quantum computing is less about immediate impact and more about long-term potential, with steady progress shaping what may eventually become a powerful complement to classical systems over time through continued research and engineering advances. Hybrid quantum classical systems. Another key idea is that quantum computers don't work alone. The most practical systems today are hybrid systems, where quantum and classical computers work together. In this setup, classical computers handle most of the work, like data processing, control systems, and analysis. Quantum processors are used only for very specific calculations. Think of it less like a replacement and more like a partnership. This approach allows researchers to take advantage of quantum capabilities while relying on the stability and power of classical systems. It's also the foundation for nearly all real-world quantum applications being explored today. Limitations and misconceptions. With all of this in mind, it's important to address a common misconception. Quantum computing is not ready for everyday use. Despite what headlines sometimes suggest, the technology is still in an experimental stage. There are major challenges that still need to be solved, including error correction, scaling up systems, and maintaining stability. Right now, most quantum applications are still in research, not deployment. So, when people talk about being quantum ready, it doesn't mean replacing current systems. It means learning how the technology works, understanding its limitations, and preparing for how it might be used in the future. A realistic understanding is essential, not just for accuracy, but for responsible decision-making. Using quantum computing today isn't really about power. It's about preparation. Researchers, companies, and governments are learning how to work with these systems before they become more advanced and widely available. Because the goal isn't just to build powerful technology, it's to understand how to use it responsibly when the time comes. And that starts with seeing quantum computing for what it is today, not what we imagine it to be.